The next battle in artificial intelligence may not be fought inside software. It may be fought inside power plants, substations, data centers, and transmission lines. Because AI does not just need chips. It needs electricity. And the future of artificial intelligence may depend on who can keep the machines powered. Artificial intelligence is usually described as a software revolution. A smarter model, a faster chatbot, a better image generator, a more capable digital assistant. From the outside, AI looks clean, fast, and invisible. But underneath that smooth interface lies something much heavier. Artificial intelligence is becoming an infrastructure system. And infrastructure systems run on power. This is the hidden reality of the AI boom. Every major AI advance depends on computation. Computation depends on hardware. And hardware at scale depends on electricity. The larger the models become, the larger the physical systems behind them become. More GPUs, more servers, more cooling, more networking, more data center capacity, more electricity. That is why the next phase of AI is not only a software race. It is also a power race. To understand why, we have to understand how modern AI systems work. Large AI models are trained through repeated mathematical computation. They process huge quantities of data. They detect patterns. They adjust internal parameters. And they repeat this process over and over again. That requires enormous machine capacity. A normal computer is not enough. Even a powerful workstation is not enough. Modern AI training happens in large compute clusters built from specialized processors, especially GPUs. Graphics processing units became essential because neural networks need parallel computation at massive scale. A CPU is flexible, but sequential. A GPU is built to perform many similar calculations at the same time. That makes GPUs much better for large machine learning workloads. As AI models became larger, companies needed bigger GPU environments. Then they needed larger data centers. Then more energy. Then more cooling. Then better infrastructure around all of it. This is how AI turned into an energy problem. The energy cost of AI does not come from one processor alone. It comes from the full system. The chip uses power. The server uses power. The storage layer uses power. The network uses power. The cooling layer uses power. The backup systems use power. The building itself uses power. That means AI must be understood as an infrastructure load, not just as software. This becomes clearer when we divide AI into its two major phases: training and inference. Training is when the model is built or improved. This is one of the most energy-intensive phases because very large clusters operate for long periods at high utilization. Inference is what happens after training. This is the live use of the model. A user asks a question. A company runs a workflow. A service generates an answer. A platform serves millions of requests. Each individual request may look small, but at scale, inference creates continuous demand. That means AI creates both concentrated energy demand and persistent energy demand. Training creates large bursts. Inference creates permanent load. Together, they make electricity a strategic variable. That is why major technology companies are no longer thinking only like software companies. They are thinking like infrastructure companies. They need chip supply. They need data center capacity. They need utility agreements. They need cooling strategies. They need reliable power access. They need expansion room. And this changes the whole competition. The winners in AI may not simply be the firms with the smartest models. They may also be the firms with the strongest infrastructure position. The firms that can secure enough electricity. The firms that can build enough compute capacity. The firms that can expand quickly without waiting years for physical upgrades. This is where the energy war behind AI begins. Not as a military war, but as a struggle over bottlenecks. Who gets enough power? Who gets enough data center capacity? Who secures the best locations? Who gets delayed by infrastructure constraints? Who can move fastest in a world where power systems do not scale at software speed? This matters because AI infrastructure is extremely power dense. A modern AI data center is not an ordinary digital facility. It is a high-intensity electrical environment. Rows of racks filled with accelerators. Large volumes of heat. Cooling systems working continuously. Power systems delivering stable electricity into dense hardware clusters. Monitoring systems keeping everything under control. As compute density rises, everything around the compute becomes harder. More heat must be removed. More electricity must be supplied. More redundancy must be built. More engineering must be coordinated. This creates a loop. More compute means more power. More power means more heat. More heat means more cooling. More cooling means even more electricity. That loop is one of the central dynamics of the AI age. It means scale becomes expensive fast. And it means the AI race is constrained by physical systems, not just software ambition. This also introduces geography into the problem. Not every region can support large-scale AI expansion equally. Some places have stronger electricity grids. Some have lower power prices. Some have more available land. Some have better cooling conditions. Some have better industrial logistics. Some have faster approval systems for infrastructure growth. That means the geography of AI increasingly follows the geography of power. This is a major shift. For years, digital technology often seemed detached from physical limits. AI changes that. AI brings digital ambition back into contact with industrial reality. Power plants, substation, transmission lines, cooling loops, construction schedules, utility constraints. These are no longer side issues. They are becoming central to AI growth. This is one reason Reuters and industry leaders have focused so much on power and data center strain. The real concern is simple. AI demand is rising faster than many parts of the physical energy system can adapt. That creates tension, because AI firms want speed. But energy infrastructure moves more slowly. A model can improve quickly. A data center can sometimes be built relatively quickly. But major power upgrades, transmission projects, and utility-scale infrastructure often take much longer. This mismatch may become one of the defining bottlenecks of the industry. And that is why the phrase energy war behind AI is not exaggeration. It describes a race over hidden limits. The public sees the model. The real battle may be happening beneath it. In the contracts, in the substations, in the cooling systems, in the facility designs, in the utility negotiations, in the race to secure enough power before the next wave of AI expansion arrives. This also explains why energy efficiency is becoming so important. If AI systems require huge amounts of electricity, then efficiency becomes a strategic advantage. A better chip reduces energy per calculation. A better cooling system reduces thermal overhead. A better model architecture reduces compute waste. A better data center design reduces operating burden. This means the future of AI may depend not only on who builds larger models, but on who builds more efficient systems. Efficiency is no longer just an engineering bonus. It may become a competitive weapon. The same is true for energy sourcing. As data center demand rises, questions about generation become more important. Where will the electricity come from? Can grids handle new AI demand? Will power be clean, cheap, and stable enough? Can capacity be added fast enough? These questions matter because AI growth is not free. It requires capital, land, machines, heat management, and electricity at industrial scale. That is the central truth. Artificial intelligence may feel lightweight to the user, but at scale, it is physically heavy. Heavy in infrastructure, high energy demand, heavy in cooling, heavy in cost, heavy in deployment complexity. That is why the next major limit on AI may not be intelligence itself. It may be whether the physical world can support the ambitions of the digital one. And that is why power now sits at the center of the AI race. Not as a background utility, but as a strategic resource. The future of artificial intelligence will not be shaped only by algorithms. It will also be shaped by who can build, power, and sustain the machines behind them. Because the next great AI bottleneck may not be the model. It may be the grid.